In this section, we're talking about congruence transformations, and all a congruence transformation is the composition of isometries, meaning it's a combination of rigid motions. Now, rigid motions are translations, reflections, and rotations. So it's just a combination of those. You might be asked to rotate a figure, then translate it. And that's a congruence transformation. You're doing more than one. And we know that two figures are congruent if there's a congruence transformation that moves one figure onto the other. They do not match up using rigid motions, then they aren't congruent. Again, you'll notice that there's absolutely no dilations. Because remember, dilations change the size of a figure, so it makes it bigger or smaller. So that wouldn't be a congruence transformation because you're changing the size. So we'll talk about that more tomorrow with similarity transformations. So we look at this first example. We have triangle text, and we want to determine the image of this triangle after we first do a rotation of 180 degrees, and then we reflect it over the line y equals 2. We'll first plot these points. Plot negative 5, 2, negative 1, 3, and negative 2, 1. Plot and label. That's super important too. Okay. Plot that image for pre-image. And the first thing we're going to do is we're going to rotate it 180 degrees. Well, how do we rotate something 180 degrees? Do we flip the point at all? No. What just happens to the signs of both values? Change. So for t, we have negative 5, 2. You do not flip the point with 180 degrees. You just change the signs. So I'm going to color coordinate this a little bit better. Green. Right. So E is negative 1, 3. When we do a 180 degree rotation, we don't flip it, we just change the sign. So negative 1, 3 becomes what? 1, negative 3. Good. And then X was negative 2, 1. So we do a 180 degree rotation, it's going to become what? 2, negative 1. You just change the sign. Okay, we'll plot those new points. Sometimes it helps if you do have a different color, like a colored pencil or something. So we're going to plot these new points. 5, negative 2. So that was T. 1, negative 3. That would be. And then 2, negative 1. That was X. And that's not our image. Okay? That was just what it's going to look like after we do the first transformation. Our image is what we do after our last transformation. So I like to just kind of highlight it with a dotted line. I still relabel it with the points so I know which one's which. But that's why it's super important we remember to put those prime marks on our final image so we know which one is the final. So if you don't label anything, we don't know if you know which one's the correct image. So you have to label with the points and the prime marks when you're done. That way you get all your points.
So you have to do the dotted lines as well?
You don't have to. I just like to do dotted. You don't have to do it. It might help to do a dotted to distinguish which one. So you could do different colors.
So you just do like the X1 and the T1.
You can do prime and then your final one's double prime, but we're not done transforming this figure. So that's why I just do the dotted because it's telling you I'm not done yet. So after we do the rotation, our next transformation is reflected over the line y equals negative 2. Well, I'm going to highlight that line. Here's where y is negative 2, and my line's going to go just through that. It's really tempting to put it up and down, but if you put it up and down, you're doing the y-axis. we only want -2, so it's going to go across. So when we reflect, remember we're just counting. So E, how far is E away from that line? E is, if we all can count, E is,
Oh,
yeah, 1. When you count, it is 1 away from that line. So you're going to go 1 away from that on the other direction. How far is X away from that line when you count?
you guys are counting helps out a little bit.
Yep, just shout it out. 1. So you go 1 in the other direction. With T, is T already sitting on that line? Yeah, so do we need to move it at all? No, when it's already sitting on the line you're reflecting over, it just kind of stays put. You don't move it. That's just going to stay at T. And then label with your prime. So E prime, T prime, X prime. So we know that you know that that's your final image. And then you just connect. That's why it's really important, because sometimes they're kind of all sitting on top of one another. And you need to make sure you very well distinguish which one's your final image. Sometimes using different color, dotted lines, darkening your final image, putting your prime marks, so we know. Questions over that one?
Okay. All right. Well, if it tells us how to do it, you guys are pretty good at that. You can figure that out. It tells me to do a rotation, then to reflect it. Well, what if we got to figure out what's going on? Well, we have to figure out how do we get one image to the other. How do I do that? What do I need to do? So determine the congruence transformation that maps triangle JQV to triangle EWT. Well, if you look above it, we have something that's very helpful to us. We're telling you, or they're telling you, that triangle JKV is congruent to triangle EWT. I know they're exactly the same. You know they're exactly the same. It says it. So how do I get them to be mapped onto one another? If I want to move one shape to the other, how do I get there? Let's figure it out. It doesn't matter. Where do you want to start? So, determine going from JQV to there. So JQV, right there. I want to map the black triangle onto the blue triangle. How do I do that? Well, you have an idea. What's your idea? 180-degree rotation. That'd be fantastic.
Because if you reflected, it would be on the same side.
It would be on the same side. We want to map this black one to be exactly like the blue one. Let's go back to the 180 a second though. Not a bad idea. 180 would definitely send it to that quadrant up there, because 180 takes you diagonally. Well, let's look at the points a little closely here. If I say angle or J, point J, where does point J match up with the other triangle? E. J matches with E. They're the same location. J's here, E's up there. Q matches up with W, Q and W, and then V matches up with T. Well, E and J, if you're thinking about it, they're both on the top, right? E's up here, J's up there. If I do the 180, like you said, which is a great idea, that would flip that J upside down, right? It'd be in the right quadrant, but it would be upside down. We don't want that. So we got to do another way of getting it here. Also, hold on a second, Jason. We know that V and T match up. Well, look, V's on this side, the right side. T's on the left side. So what do you do? Jason, you have an idea?
You do a reflection over x equals y.
X equals y. I see what you're saying. You want to reflect over the y-axis. Is that what you're saying?
No, like where x equals y, like 1, 1, 2, 2. Like the diagonal.
The diagonal would be y equals x, is what you're thinking, right?
Oh.
Y equals x is that one. And that's not a bad idea, but it's flipped. But I like your reflection thing a lot. The reflection, the diagonal, the y equals x, is going to be diagonal line. They're not really near to one another because they're oriented differently. But I really do like your flipping. Now, yes, Alexia?
Would it be a reflection over the y-axis?
Because, yes, we're going to do the reflection of the y. If you do over X, it's just like we did a second ago. That J would be pointing down. We want it to be facing up. So the only way we can do it is flip it over to the Y-axis. So we are going to do a reflection. What letter represents a reflection? Capital R. They can say the capital in there. So we say we're doing a capital R. We are reflecting, you guys told me, across the Y-axis. So let's go ahead and do that. We like to highlight where we're at, so we can see that line. I want to reflect. Again, have colored pencils, highlighters, really helps you visualize these things a lot better. Well, let's look at Q. How far away is Q from that line of symmetry that we're flipping across? 1. So I'm going to go 1. 1 in the other direction. That's my Q. Q prime, everyone think about it. What about J? How far away is J from there? 2 down. 1, 2, 1, 2. J. V is this number 5. 1, 2, 3, 4, 5. There is V. All right, cool. Well, obviously, that newly reflected thing is not in the same location as the blue one. But now they're oriented the same way, meaning they're facing the same way. The J's on top, E's on top. V's over here to the left, T's over here to the left. Q's on the right side, W's on the right side. They're on the right area, but they're not sitting on each other. I need to do one last thing. Jason?
A transformation, whatever it's called.
Translation, there you go. That's the slide one. You're right, though. I want to slide it over there. So here's what it's going to do. We're doing a reflection first, then you have this little degree symbol. It's like a little dot, open dot. So open dot. And then Jason said we're doing translation. We are going to do a translation. That's represented by a capital T. Now, again, when we do this, we do X first. We go left to right first, then we got to go up or down. How far left or right in the X direction do we need to go? 0. Because if you look at it, they're on pace with one another. So I go 0, but I always have to go up or down to get to the other shape. So which direction do I have to go? Up. How much? Well, we'll find out. Just count the difference. 1, 2, 3, 4, 5. That's good for T's. Still, always check the other points. 1, 2, 3, 4, 5. That's good for J to E. And Q to W. Let's see. 1, 2, 3, 4, 5. They are the same. And since I went up, it is going to be positive. Good. So there is my congruent transformation right there. So I know that I first did a reflection, and then I did a translation at that degree. Now, what did we move? We moved triangle J, Q, V. And this is how your statement's going to look. The thing inside the parentheses, what your moves are, and then the thing outside of it, behind it, is going to be what you move. Questions with that? Again, some of you say, oh, this is difficult. The more you do this, the better you get with it. You say, oh, well, I know it's got to do this and this. There's also more than one way to do this. You could have translated it first. You could have slid it and then reflected it. You just have to know a little bit more. I could have slid this up and then reflected over it.
With the other ones.
You could have done, yeah, you could have done lots of things with it. It told us to go from JQV to the other one, but there's other ways of getting there. So let's ask some questions here about this congruent thing here. These congruent transformations. What happens? All right. So when we move these shapes around, does the measured angle J and the measured E change? If I'm moving it, sliding it, if I flipped it and slid it, do they change? No, they stay the same thing. So these remain the same thing. So the angles stay the same. They always will. What about some segments? What about segment VQ and TW? Do those remain the same? VQ's right here, TW's right there, so they match up. Do they remain the same no matter how I move them around? Yeah, they're still the same. Their measures are the same, so same on that one. Good. What about the perimeter, the perimeter? Does the perimeter change if I'm just sliding it around, flipping it around? No, perimeter's going to stay the same as well. Same. Area. Is the area going to change? Yes? Correct answer is Yeah, they're the same. Whoop! My color coordinating went out the window. Same. All right. I think I know what this one's going to be. I have a guess, but I don't know yet. What are the slopes of the lines of JV and ET? Are the slopes going to change? Different?
Because when you flip them, they become negative.
Their slopes are still the lines of JV and ET. Since they still match up, their slopes will still, the orientation will be the same.
Wouldn't it be like negative?
Before you flipped them, Jason, the slopes were opposite. Flipped it, and you aligned the slopes.
Yep, they'll be back the same once you move it around. Once you do your transformations. All right, questions on that? All right, let's try another one. Let's try to get the hang of this. Let's determine what pairs are congruent.
Okay, if we look at example 3, we're going to see if these figures are congruent and how they would map up onto one another so that they are. So let's take a look at the triangles first. Okay, and a lot of the times when you do these, figure out how can I get these oriented the same. That's how I like to approach it. So if we look at this triangle, we'll move the top triangle. Really, if you're doing this on your own, it doesn't matter which one. So if we get started, we'll move this top triangle. So if you notice, this part of the triangle is pointing up, and this part of the triangle is pointing down. So what do you think we need to do to get them pointing in the same direction? What's your? Yeah, reflection over what? It would just be what lines in between these two triangles? X. So we're going to flip over the x-axis. That's the line that's in between them currently. Oh, heck. So that's what we're going to flip over. Okay. So again, when we do a reflection, we just count. 1, 1, 1, 1. E is 1, 2, 3, 4, 5. We go 1, 2, 3, 4, 5. So we flipped it. And we're going to write that down. For the triangles, we reflected it over the x-axis. Okay. Did they match up when we did that? No. They didn't match up. So they're both pointing down. But if you notice, this part of the triangle is pointing this way, and this triangle is pointing the other way. So, Jake, what can we do to get them pointing in the same direction? Perfect. We can reflect over the y-axis. So we can reflect again over that axis. So when we do so, again, just count. 1, 1. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Matches up. And 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. So all these vertices match up. Triangles match up on one another. So would these triangles be congruent? Yeah. Alright, so let's finish. We did a reflection over the x-axis. Then we did a reflection over the y-axis. And which triangle did we move? Yeah, so we say triangle E, D, F. So we know those triangles are congruent. Another thing you could have done one single transformation. Whenever you have a double reflection like that, what else have you done? It's tempting. That only works for one point. So in order to do that, it has to work for all. So it's tempting. We have a double reflection. That's the same as a rotation of 180 degrees. So you might notice in your brain, you might be thinking, well, I need to flip it, and then I need to flip it again. Whenever you're doing that, when you're trying to figure out what your mapping is, if you're doing a double reflection, it's just a rotation of 180 degrees. So you could have just done that, and it would have matched up.
Why wouldn't x equals y work?
If you look at that line, y equals x. Here. It works for one point. If you look at f, it's 1, 2, 1, 2. But if you look at d, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it doesn't necessarily
I thought.
match up.
Well, I thought D would match up with L.
Yep, that's why, because we went.
Yeah, D needs to go with L.
Yep.
So
it's
in
all
order
the
to
way
be at
down
180,
here.
L would have to be where that one's at.
Yeah. So that's why that line doesn't work, because when we do it, they get super disoriented.
Yeah, the orientation of that would change.
Yeah.
You're split, think of like a mirrored image. So that D has to be to the lower left, and L would have to be the lower left.
So if you flipped it, yeah, these would match up, but then those other sides wouldn't. So it wouldn't really work out. Okay, let's take a look at, don't do that. Mapping up the trapezoids. Okay? So if we look, you notice this top trapezoid is pointing to the right, and the bottom trapezoid is pointing to the left. So whenever they're pointing in different directions, what transformation do we need to do? When our triangles were pointing in different directions, what were our transformations? What were the two transformations we just did when they were pointing in the same direction? What did we do in that first one? When they weren't pointing in the same direction? What does capital R stand for? Reflection. Okay? So when they're not pointing in the same direction, that should indicate to you that you are doing a reflection. So this one's pointing to the right, this one's pointing to the left. That's indicating to you that I need to reflect it. Okay? And do we want to move the bottom trapezoid or the top trapezoid? Okay, move the top one. What do you think we need to reflect over to move the top one? Yeah, the y-axis. You need to flip it over there. So kind of lonely. This one looks like it's in between. If you flip it over that one, I think it would still work out. We can flip it over the y. So we flip it over the y. Again, just count. 1, 1. 1, 2, 3. 1, 2. 1, 2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Again, this point y right here is sitting on the axis, so it doesn't move. It's just going to stay there. Okay. So they're now pointing and oriented in the same direction. So we need to get them to match up. So how are you going to get them to match up? We don't need to flip or rotate anything. So we just need to slide. What's the same as sliding? Translation. Right? So I'm going to write what we just did. We did a reflection over the y-axis. Once we get them oriented in the same direction, we just need to slide. Well, we said a translation was the same as a slide. Okay? Do we need to move right or left to get these lined up? Yeah, so it's going to be negative. How far to the left do we have to move it? 1. We want left 1. Okay. Do we need to move it up or down to get these to match up? How far do we move down? So check all the other points just in case. The left 1, down 1, 2, 3, 4, 5. Matches up. Left 1, down 1, 2, 3, 4, 5. Matches up. Left 1, down 1, 2, 3, 4, 5. Okay. And then what figure did we move? What are the vertices of the figure we moved?
Okay, walking around suddenly, you guys are going branching off your own, which is great. And you may have done differently. For with Evan over there, he went for the bottom trapezoid, and his were different. He did the translation first, he didn't flip it. Like, there's different ways to get this, you'll still get the same answer. So again, it doesn't matter if you do translation first or reflection. Just gotta make sure you're doing the same thing before.
And even this one, you could have just done a 180-degree rotation and it's correct. So there's a lot of times there's more than one answer that you're not wrong, as long as they're matching up.
There's sometimes you guys will take them longer, like, oh, never thought of it that way. Good
Yeah.
job.
Okay. Last one, we want to get these segments to match up. So if you look at the segments, are they oriented the same way? Are the slopes kind of going in the same direction? Yeah, so you don't need to flip or rotate anything. So what's the only thing we need to do? Yeah, very good. All we have to do is a translation. When they're already oriented, you just need to slide them. Right, so we know we're going to do a translation. How far do we have to move across to get them to line up? Good, 2. And do we go to the left or the right? To the right, so it's going to be a positive 2. And then do we have to move up or down to get them to match up? Down. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So we went down 9. So it's going to be negative. Again, just double check the other one. 1, 2. And then if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, it matches up. We don't really need this parenthesis because we only did 1. Okay? And then we move segment PQ. Whatever figure you move, it's really important that that's what you're putting in your parentheses. That way the figure matches the transformation. Again, you could have moved HG and said right to up 9. That's totally fine, as long as this is correct. And that's correct.